This question asks us to find the first four terms of the given sequence. The sequence is defined a little bit differently than in the past. What we see here is a formula for the n plus first term if we know the nth term. So in other words, if I know the term that I'm at, this tells me how to get to the next one. So if I know an, then I can figure out what an plus 1 is. This is called a recurrence relation. It tells us how to find the next term in the sequence. This is good in some senses, but it can be also more challenging in others. Right? If I ask you for the 1000th term of this sequence, well, it's not obvious how to get that from here, because I'd have to go through and find the first and the second and then the third and so on and so on and so on. So it's, in that sense, it's not as nice as having a formula, an explicit formula. But we'll see that we can use this to find the explicit formula in some cases. But in this example, all we want is the first four terms. We also are told the starting value. Since a1 is 7, then a2 I'm going to get by using this recurrence relation. And a2 is negative 3a1. That's all that says. The next term is negative 3 times the previous term. So that's negative 3 times 7, which is negative 21. And from here on out, it's just as simple. Each time we're going to simply multiply by negative 3. This will be negative 3a2, which is negative 3 times negative 21, which is positive 63. And a4 will be negative 3a3, which is negative 3 times 63, which is negative 189. In this problem, we're given an explicit formula for the terms of an. An is 10 to the n minus 5. We'd like the first four terms, and then we'd like to ask, what does it converge to, if anything? So let's just start. a1 is 10 to the 1 minus 5, which is 10 minus 5, which is 5. a2 will be 10 squared minus 5, which is 95. a3 will be 10 cubed minus 5, which is 1000 minus 5, which is 995. a4 is 10 to the 4th minus 5, which will be 10,000 minus 5, which will be 9,995. These are the first four terms. When I say, what does it converge to, I'm asking, what do these numbers get closer and closer to, if anything? We need the numbers to squeeze down closer and closer and closer to something, if that's going to happen at all. These numbers are just getting bigger and bigger and bigger and bigger, and will continue to get bigger forever. And in fact, will go all the way to infinity. So this one does not converge, which means that it diverges. Diverge, remember, can mean one of two things. It can mean that it goes to infinity or negative infinity, which is what's happening in this case, or it could be something that just does not get closer and closer and closer to a single value. Maybe it oscillates, maybe it does some other weird stuff where it just does not converge down to a single value. So the diverge takes both of those things into account. That word means both, one or the other. This question asks us to find the first four terms of the given sequence. The sequence is defined a little bit differently than in the past. What we see here is a formula for the n plus first term if we know the nth term. So in other words, if I know the term that I'm at, this tells me how to get to the next one. So if I know an, then I can figure out what an plus 1 is. This is called a recurrence relation. It tells us how to find the next term in the sequence. This is good in some senses, but it can be also more challenging in others. Right? If I ask you for the 1000th term of this sequence, well, it's not obvious how to get that from here, because I'd have to go through and find the first and the second and then the third and so on and so on and so on. So it's, in that sense, it's not as nice as having a formula, an explicit formula. But we'll see that we can use this to find the explicit formula in some cases. But in this example, all we want is the first four terms. We also are told the starting value. Since a1 is 7, then A2 I'm going to get by using this recurrence relation. And A2 is negative 3A1. That's all that says. The next term is negative 3 times the previous term. So that's negative 3 times 7, which is negative 21. And from here on out, it's just as simple. Each time we're going to simply multiply by negative 3. This will be negative 3A2, which is negative 3 times negative 21, which is positive 63. And A4 will be negative 3A3, which is negative 3 times 63, which is negative 189. In this question, we're given a sequence described as above, a pattern, 8, negative 8, 8, negative 8, 8, negative 8, and so on, and asked to do a few things with this sequence. First, we have the first 5 terms. We'd like to know what is the 6th term and the 7th term. There's not much to that. This is just switching back and forth, alternating between 8 and negative 8. Since we're at 8, the next term will be negative 8, and the next term after that will be 8. Next, what is a recurrence formula? Remember, a recurrence formula will have a formula for the nth term, n plus first term, and it will include somehow or another a n here, or possibly even earlier ones. And we'll also need the starting value. Well, a1 is 8. How do I go from one term to the next? No matter where I am, I go from one term to the next by multiplying by negative 1. So the n plus first term is the negative of the nth term. And this is the recurrence relation. Finally, we would like an explicit formula. That is, I want an equals something that gives me a formula in terms of n that tells me the value of the sequence no matter where I am. Well, these are clearly 8s, so it's going to be 8. I'd like something that's going to make it alternate between positive and negative, positive and negative. The idea is that if I have negative 1 to a power, if it's negative 1 to an even power, that's positive 1. If it's negative 1 to an odd power, that's negative 1. So what we're going to have, and this is going to be something that we'll see all the time in the future, is negative 1 to a power. The issue is I can't just plug an n here, because if I put negative 1 to the n, then when n is 1, I'm going to get negative 1 to the 1, which is negative. So that would tell me if I just did that, then the very first term would be negative, and that's not what we're given. So we can't just do this. This will make it alternating, but it doesn't start with the right sign. So to fix that, we need to put a plus 1 in here. Because now if I plug 1 in for n, I get negative 1 squared, which is positive. So the first term is positive 8, as we need. In this problem, we are given a sequence defined by a pattern, as we see here, and asked for some information about the sequence. Here are the first 5 terms, 2, 6, 10, 14, 18. The next term, a6, well, the pattern says add 4 each time. So the next one should be 22, and the one after that should be 26. That way of describing it also tells us what's happening with the recurrence relation. If I'm adding 4 each time, that means that an plus 1 had better be an plus 4. I take the previous term, I add 4 to it, and that gets me the next term. But remember, with a recurrence relation, we also need to give you the starting value, and the starting value is 2. What is an explicit formula for an? In other words, if I give you n, can you tell me what the sequence term is? If I want to know the millionth term, then I can't really use a recurrence relation because I'd have to go through all million terms. I'd like to be able to just find the millionth term just from a formula. So what's happening? Well, we're adding 4 each time, but we're starting at 2. So adding 4 each time should indicate that we have multiples of 4. So let's think about that. Let's use that. Multiples of 4. 4n. So that's 4, that's 8, that's 12, and so on and so on and so on. What's the difference between those numbers that I've just read and what we have here? Well, the difference is that we're 2 off. We need to subtract 2. If I have 4, 8, 10, and then minus 2, that's going to get me, 4, 8, 12. Minus 2 will get me 2, 6, 10, and so on and so on and so on. Starting at n equal to 1. Now there are alternate ways of writing this that are still correct. We could have instead thought, well, let's start at 2. We'd like to add multiples of 4, but I can't just say 4n, because when n is 1, that would start me at 6. So I actually need to back that off a little bit. So I start at 2, look at multiples of 4, but let's use n. When I plug 1 in for n, I don't want any multiples of 4. I want that to be 0. So plugging 1 in for n will make that go away, leaving me with just 2. So that's a different way to write it. There are even other ways that you could write it. There's not just a single correct answer up here for part C. In this problem, we're given the sequence an is 10 to the n minus 5. What we're going to do is we're going to write down the first 4 terms. a1 will be 10 to the first minus 5, which is 5. a2 is 10 squared minus 5, which is 95, 100 minus 5. a3 will be 10 cubed, 1,000 minus 5, which is 995. a4 will be 10,000 minus 5, 9,995. These numbers are obviously getting really big. This is going to get very, very big as well. If we had to make a plausible guess for the limit as n goes to infinity of an, I would say that this limit is infinity. This limit does not exist. It doesn't go to some finite number. It's going to go all the way up to infinity. So what that means is this sequence diverges. It does not converge. It does not have a limit. And so let's just think about what's happening when I plug in large values of n. When I'm saying the limit as n goes to infinity, I'm saying n is going to infinity. So n is going to get huge, extremely big. If n is huge, what's happening here? This is 108n minus 1, which is essentially 108n. If n is really, really big, I almost don't even see that minus 1 on the numerator. And the denominator will be 12 times n. So when n is huge, really all that's happening is I don't have that minus 1 there. I don't care about it because the difference is almost negligible. It's like a billion and versus a billion and 1. You don't notice, and when n gets even bigger, you notice even less. And so that difference goes away completely. All right, so what's happening here when n goes to infinity is that all I care about are the biggest terms, biggest degree term in the numerator and the biggest degree term in the denominator. The smaller degree stuff doesn't contribute. That's whether it's a polynomial, and then we'll also see that we can compare different functions as well. But for now, that minus 1 plays essentially no role, and this limit will be 108n over 12n. The n's cancel, and I get 108 over 12. Let's see, what's that? 9. 12 times 10 will be 120, 12 times 9 is 108. So that is the limit. Another way that you can look at this is you could plug in values of n. You could plug in very big values of n into this and put it into a calculator and see what you get. You'll find that you'll get stuff that is very close to 9, and as n gets bigger and bigger and bigger, they get closer and closer to 9 as well. In this problem, we are given a sequence defined by the recurrence relation, and we'd like to find the limit as n goes to infinity of an. So we're told where to start, and given this, we can find the next value. We can always find the next value. So we're going to do this 2 ways. First, we're going to write down a bunch of terms. We're going to determine the value of an for a bunch of terms and look for a pattern, see where it's headed, and then I'll show you an alternate way of thinking about this as well. Okay, so that's what we want. So a1, a0 we're told is 7, so let's start there. a0 is 7. So a1 is going to be 1/4 times a0, which is 7, plus 6. And for this problem, it will be convenient to have a calculator that can deal with fractions and simplify them. So we want 1/4 times 7 plus 6. And you want to make sure that you have that as a fraction. and that's 31 over 4. Now, if you put this into your calculator correctly, we can start making these next values without very much work at all by saying that A2 is 1/4 of the previous answer, right? So this is AN, so that will be 31 over 4 plus 6. So I can just put in my calculator 1/4 times the answer that it just calculated, and then plus 6. So that's what I'm going to do. I'm going to do 1/4 multiplied by the answer. Remember that on the TI-8384, that second enter, that will bring up, or second answer, that's down by the decimal point, sorry, second answer down by the decimal point. So 1/4 times the answer plus 6, and then hit enter. Make sure you're converting it to the fractions, and so that is 127 over 16. 127 over 16. And the next one and so we'll find that we get 511 over 64. And if we keep going, I'll find that A4 is 2047 over 256. And A5 is 4095 divided by 1024. And we're going to start looking for a pattern just at this point. The denominators work out pretty nicely. This is 4, this is 16. Look what we're doing. We're multiplying by 4 each time to get to the next denominator. I'm going to think about that in a slightly different way. I'm going to write 7 as 7 over 1. And then I'm going to think about these as powers of 2. This is 2 to the 0. This is 2 squared. This is 2 to the 4th. This is 2 to the 6th. So the denominators here are even powers of 2. So this is 2 to the 2n. You could think about that as 4 to the n as well. It works out to be the same thing. But these are even powers of 2. 2, 0, 2 squared, 2, 4, 2, 6, and so on. The numerators are a little harder to see, but you should think about this as the 7, 31, 127. I'm looking as very similar to 8, 32, 128, which are also powers of 2. This is 2 cubed. This is 2 to the 5th. This is 2 to the 7th. So now it's odd powers of 2, but then we have to take 1 away from them. So we're seeing odd powers of 2 and then taking away 1. We just have to be careful that they are going to match up with what we've written down here. What was the very first n value? We decided that based on my denominator, I'm starting at n equals 0, because if I plug 0 in for n, I will get 2 to the 0, which is 1. So if I'm starting at n equals 0, I need to end up getting 3 as my first power of 2. That means that I'm going to need 2 to the 2n plus 3. Now that's always going to be odd because 2n is always going to be even. So this is always even plus 3, which will be an odd number, and will always get me to the next odd number. It's just like 2n plus 1, but the fact that I have a 3 in here just means that I'm jumping to the next odd one to start. Notice when I plug n equals 0 in, then that becomes 2 to the 3, which is the 8 that I need it to be, but then I'm subtracting 1. Okay, so now when I plug n equals 0 in, just to be clear, n equals 0 makes 2 to the 3 minus 1, that's 8 minus 1, which is 7, like I need it to be. And then the denominator is 2 to the 0, which is 1, like I need it to be. If I plug n equal 1 in, then I get 2 to the 5, which is 32. Minus 1 makes the 31 that we see. Plugging n equal 1 in down here makes 2 to the 4, which is the 4 that we need. and the rest of these will also all work out as necessary. So this is an explicit formula for AN. We've just found an explicit formula for AN by writing down the numbers and looking for a pattern. Okay, so now what? Now we're asked, what is the limit of this as n goes to infinity? So let me save this formula. I want the limit as n goes to infinity of 2 to the 2n plus 3 minus 1 over 2 to the 2n. Let's just do some algebra. That 2n plus 3, that's 2 to the 2n times 2 cubed minus 1 over 2n. 2 to the 2n. Right, that's how the exponents work. This is 2 to the n, this is 3. I can add them up to make 2n plus 3. So we're still looking at that limit. Now I'm going to divide this into both pieces to say limit as n goes to infinity of 2 to the n times 2 to the 3 over 2 to the 2n, to the 2n up there, sorry, over 2 to the 2n minus 1 over 2 to the 2n. The limit as n goes to infinity. These cancel, and I'm left with limit as n goes to infinity of 2 cubed. What happens when n goes to infinity here? This goes to 0, minus 0. And so in the end I'm going to get 8 as my final limit. Now, let me show you an alternate way of thinking about that, which actually is easier. It's easier to do the calculations, maybe a bit harder to understand the idea. An alternate way of thinking about this is to take this an plus 1 as 1/4 an plus 6 and take the limit, let me leave some space here, what I want to do is take the limit as n goes to infinity of both sides. The idea here is that the limit of the n plus first terms is the same as the limit of the nth terms. This is just one ahead, it's always one step ahead, but when I take the limit, I'm just getting to the limit in the very end. So these things are exactly the same. So I can think about this as, so first let's just say this. I'm going to distribute this limit, which I'm allowed to do because this is just a sum. The limit of a sum is the sum of the limits. I can bring the 1/4 out. And the limit of 6 is just 6. And the point here, again, is that limit as n goes to infinity of an plus 1 is just the same as the limit as n goes to infinity of an. The limit is the same. So this thing is the same as this thing, so just to simplify my life a little bit, let me just call that x, so I don't have to keep writing limit. So that's x is equal to 1/4 x plus 6. So if you want to skip all of this writing of the limit, really all that we did was we thought about an plus 1 as being the same as an, and the limit becomes x, and we have x is equal to 1/4 x plus 6. So if x is equal to 1/4 x plus 6, and we solve for x, we bring the 1/4 over, that becomes 3/4 x is equal to 6. So that x is equal to 6 times 4/3, which is 24/3, which is 8, which is exactly the same limit that we came up with by writing out a bunch of terms and looking for a pattern. And then doing some algebra. This is much easier in the end. But hopefully putting the two together convinces you that they're both reasonable ways to approach the problem. In this question, we're given an infinitely long sum. 0.1 plus 0.01 plus 0.001, and so on and so on and so on. We're going to add up an infinite amount, an infinite number of terms, and say, well, does that actually make something? It shouldn't be surprising if the answer is yes, because that should remind you of our improper integrals, where we had an integral that went all the way out to infinity, but it still might add up to a finite number. A similar thing can happen in this case. The way to approach the thinking for these problems, and this really is a formal definition that we'll look more at later, how do I add up an infinite amount of things? Well, we're going to start by saying that we're going to give these things terms, a1, a2, a3, a4, and so on and so on and so on. And what we're going to do is make what we call a sequence of partial sums. Partial sums will be add up the first set of entries, or the first set of terms in the sum. And so S1 is just going to be take the very first term. S2 will be take the first two terms. So S1 is just A1, S2 is A1 plus A2. So S for sum, this is the first partial sum. This is the second partial sum. S3 will be A1 plus A2 plus A3. S4 will be A1 plus A2 plus A3 plus A4. And so on and so on and so on. So this is going to give me a list of numbers. It's going to give me a sequence. The sequence of partial sums. S1, S2, S3, and so on and so on and so on. We say that this sum, this infinite sum, exists if this sequence of partial sums has a limit that exists. If the partial sums are getting closer and closer and closer to something, that something is the infinite sum that we started with. In this example, this works out rather nicely. 0.1, and then 0.1 plus 0.01 is 0.11. S3 will be 0.111. Each time I add up a new entry, I'm adding a 1 at a later decimal place. This is 0.111. So this total sum, 0.1 plus 0.01 plus 0.001 plus forever on out, is going to be the limit as n goes to infinity of the sequence of partial sums. Well, what's happening to these numbers as I go further and further and further down the list? I'm getting an extra 1 each time I go. In the limit, I'm going to get a 1 everywhere, which is 0.1 repeating. In this problem, we are asked to find the first 4 partial sums of this series, use that to guess at a formula for Sn, and then use that to guess at an actual value for the series. So to begin, let's start by finding A1 through A4. A1 is 1 over 11 to the first. A2 is 1 over 11 squared. A3 is 1 over 11 cubed. And A4 is 1 over 11 to the fourth. So those are the first 4 terms of the series. S1 is A1, which is 1 over 11. S2 is A1 plus A2, so that's these two things added together. 1 over 11 plus 1 over 11 squared, and I'm going to organize these in a funny looking way so that we can find a pattern in the future. If I multiply this by 11 over 11, I get 11 over 11 squared plus 1 over 11 squared, which is 11 plus 1 over 11 squared. I'm going to leave it like that. S3, A1 plus A2 plus A3. Well, A1 plus A2, we've already figured out, that's right there. That's 11 plus 1 over 11 squared. And then A3 is 1 over 11 cubed. So if I need a common denominator, that would be 11 cubed. So I need to multiply this by 11 over 11. And I get 11 times 11 plus 1 over 11 cubed plus 1 over 11 cubed. Well, that's 11 squared plus 11 plus 1. 11 squared by distributing it in, 11 by distributing in, and then adding the one that's over on the right, all over 11 cubed. That should have been an S3. My apologies. S4 will be A1 plus A2 plus A3 plus A4, which is the value that we just calculated, 11 squared plus 11 plus 1 over 11 cubed, all over plus 1 over 11 to the 4th. If we do the same thing, I'm not going to work out all the details, but if I multiply by 11 over 11 again to get a common denominator, distribute the 11 through, add everything up, I get 11 cubed plus 11 squared plus 11 plus 1, all over 11 to the 4th. So we've got S1, S2, S3, and S4 in a way that's easy to see the pattern. If you would write these all out and figure out what those numbers are, the pattern would not be obvious at all. But as it's written like this, they're fine. They are the answers to the question, but it makes it easy to guess at a formula for part B. Okay, so for part B, what do we have? Well, we're going to, the denominators will just be 11 to the n. The numerators will essentially be 1 plus 11 squared plus 11 to the n minus 1. So Sn, in terms of a formula, we're going to have 11 to the n here. We're going to have 11 to the n minus 1 plus all the way down to 11 squared plus 11 plus 1. Right, so notice that the final exponent in the numerator is 1 less than the denominator, which is exactly what I wrote right there. 11 squared all the way down to 1. Denominator is 11 to the n. So this is the answer to part B, right there. For part C, guess at the limit as n goes to infinity. As it's written, it's not obvious at all what to do, and so we need to do some algebra tricks in order to make that work out a little bit better for us. Many of these are given in the text version of the example here, so I'm not going to go through all of the gory details, but I will give you some of the basic ideas of what's happening in this algebra. We can think about this 11 to the n minus 1 all the way down to 1. I'm going to think about that as x to the n minus 1 plus x to the n minus 2 plus x cubed plus x squared plus x plus 1. I'm going to think about this as a polynomial. Think about this as a polynomial where x is equal to 11. Right, so if I plug 11 into this, then I'm going to get Sn right here. Okay, so this is just simplifies our algebra a little bit so we don't have 11s all over the place, and it really doesn't matter what the fact that this is 11. This is going to work for any value, not just 11. Okay, now here's the trick. Here's the key point. If I take the polynomial x to the n minus 1 and I divide by x minus 1, so this is a long division, a synthetic division type situation. My claim is that that's exactly what you would get. This whole piece is that numerator right there. Just to give you just a couple of quick justifications. If I took x squared minus 1 and I divided by x minus 1, well, x squared minus 1 is x minus 1, x plus 1, divided by x minus 1, and the x minus 1's canceled, and I get x plus 1 back, which is exactly what this is saying. If I start with 2, if I have x squared minus 1, then I better get just the x minus 1, the x to the 1 to start, right? 1 less than the denominator, all the way down to 1. And this actually happens no matter what. If I take x cubed minus 1 divided by x minus 1. Well, x cubed minus 1, as it turns out, you might have learned some formula at some point in an algebra class, but as it turns out, this is x minus 1 times x squared plus x plus 1. That's how a cubic, this is the difference of cubes and how it factors. The x minus 1's will cancel, leaving me with x squared plus x plus 1. And so my claim is that this is always true, no matter what, whether this is a 2 or a 3. If I take x to the n minus 1, divide by x minus 1, then I'm left with something that looks just like this, up to 1 minus wherever the starting exponent was. And so we're just going to take that as true, which means that this formula becomes x to the n minus 1 all over x minus 1 all over x to the n. Right, so that numerator is this piece right here. The denominator hasn't changed. So that's x to the n minus 1 over x minus 1 times 1 over x to the n. And now's where we'll go back and remember that x was 11. And we just use that to simplify the notation a little bit. So if x is 11, this makes 11 to the n minus 1 over 11 minus 1 times 1 over 11 to the n, which is 11 to the n minus 1 over 10 times 11 to the n. Right, all that I did was turn that 11 minus 1 into 10 and then combine my two fractions together. And this is a formula for Sn. Now finally, part C, guess at the limit. So let me put that formula up here. We found that Sn was 11 to the n minus 1 over 10 times 11 to the n. What is the limit as n goes to infinity? Or so what is the value of this series? Well, remember that we only need the terms, the biggest degree terms. If I only need the biggest degree terms, that means that this minus 1 I don't care about. As before, I'm only looking at the things which contribute the most, which in the numerator is the 11 to the n, and the denominator is 10 times 11 to the n. So that's 11 to the n over 10 times 11 to the n. The 11 to the n's will cancel, and I end up getting 1/10 as the final sum.